Somewhere in the constellation of Coma Berenices, about 300 million light-years away, something big is happening right now. Two galaxies, huge on a scale that the human brain is unable to digest normally, are slowly but unstoppably pulled into each other. Each has a supermassive black hole inside. Hundreds of billions of stars on each side, giant clouds of gas and dust, and all this is moving forward. No, there will be no explosion, at least not in the sense in which we are used to thinking about explosions. But what will happen will be much more terrible and larger. Two galaxies will literally turn each other inside out. Their gas will begin to rotate, twist, heat up to millions of degrees. Jets will fly from the centers, streams of plasma that will exceed the length of the galaxy itself by dozens of times. Millions of new stars will flare up in a negligible time by cosmic standards, and then silence will come. One huge elliptical galaxy is almost dead, almost without gas, almost without a future. This is what we will talk about today, about what happens when galaxies collide, about how jets, vortices, and something very similar to a cosmic tornado are born. Dark matter, which behaves very differently from anything else, and about what awaits us in about 4.5 billion years when the Milky Way meets the Andromeda Galaxy. But let's start from the beginning with a question that seems simple, but in fact it is not at all. How do galaxies manage to collide at all if the universe is so huge? Here's what's important to understand. When it comes to galaxies, our intuition fails us. We are used to thinking, the larger the space, the less likely it is to collide with something. Throw 2 grains of sand into the ocean, it is unlikely that they will ever meet. The logic is clear. But with galaxies, everything is different. Galaxies are not lonely islands in infinite space. They live in groups, clusters, superclusters. Our Milky Way is part of the so-called local group, which has more than 50 galaxies. Most of them are dwarfs, but there are also a few big players among them, including Andromeda, our closest major neighbor at a distance of about 2.5 million light-years. But why collisions occur at all is not just a matter of speed. It's a question of size. Galaxies are much larger relative to the distances between them than, say, stars relative to the distances between them. The diameter of the Milky Way is about 100,000 light-years. The distance to Andromeda is 2.5 million light-years. The size-to-distance ratio is approximately 1 to 25. For comparison, the diameter of our Sun is about 1.4 million kilometers, and the distance to the nearest star, Proxima Centauri, is more than 40 trillion kilometers. The ratio there is 1 to 30 million. This is why stars almost never collide directly, but galaxies very much can. And one more important point. Gravity does not know distances in the sense in which we are used to thinking of it. Two galaxies a few million light-years apart still feel each other's gravity. It is weak but constant. And for billions of years, this weak, constant attraction does its job, galaxies begin to move towards each other. They accelerate slowly, and then they can't stop. This is exactly what is happening to Andromeda. And that's exactly what has already happened or is happening right now in thousands of other places in the universe. Now let's look at what exactly happens when two galaxies begin to make contact. Because many people make mistakes here, and this mistake is understandable. When you say collision, the brain draws a picture of a frontal impact. Two huge things crash into each other and shatter to shreds, like two cars at an intersection. But the reality is completely different. When galaxies begin to approach each other, the first thing that happens is deformation. The gravitational tidal forces of one galaxy begin to pull on the stars and gas of the other. Imagine the moon pulling on the Earth's waters, creating tides. Now scale this up to the size of a galaxy. The so-called tidal tails and bridges appear, giant extended structures of stars and gas that stretch out in space. Sometimes they can stretch for hundreds of thousand light years. This is the first visual sign that two objects have begun to interact. The very process of collision is not an instant. This is several billion years. Galaxies pass through each other, diverge, attract again, pass again, diverge again. Each such passage is called a periapsis, the moment of closest approach. After the first pass, galaxies look completely different. Their structure is disturbed. The spiral arms are broken. The gas is mixed. Stars are ejected into random orbits. But the most interesting thing is that almost nothing happens to the stars physically. They do not collide. The distances between the stars are so colossal that two galaxies can literally pass through each other. And there will be practically no direct collisions of stars. Stars are just tiny dots in a vast empty space. They will change their orbits under the influence of gravity. Their trajectories will become chaotic, but most of them will survive physically. But gas is a completely different story. Gas is the substance that really suffers when galaxies collide. And it is through the gas that all the most impressive things unfold. Unlike stars, gas clouds don't just pass through each other under the influence of gravity. Gas interacts physically. When two streams of gas from different galaxies collide, shock waves occur. Blood pressure rises sharply. The temperature jumps. The gas is compressed into dense lumps. And these dense clumps are just ideal conditions for the birth of new stars. That is why during collisions of galaxies, the so-called burst of star formation, or starburst in English, is observed.
The rate of birth of new stars increases dramatically, sometimes tens or even hundreds of times compared to the norm. In our Milky Way, about 1 or 2 stars are now born per year. In galaxies experiencing a collision, this number can reach several hundred per year. This is a colossal difference.
But there is one nuance here. This star formation is a kind of suicide. The faster a galaxy gives birth to new stars, the faster it burns through its gas supply. And without gas, new stars are no longer formed. After all the gas is either used up by the stars or thrown out, the galaxy seems to extinguish the light.
Now about dark matter, because without it, the story of galaxy collisions would be incomplete and wrong. Dark matter is matter that we can't see. It does not emit light, does not absorb it, does not interact with electromagnetic radiation in any way. We only know about its existence through gravity. It attracts other objects, and this attraction can be measured. According to modern data, in a typical galaxy, ordinary matter, stars, gas, dust, makes up only about 15% of the total mass. Everything else is dark matter. It forms a huge invisible halo around the galaxy that extends far beyond the visible disk. And this is what happens to dark matter when galaxies collide. It behaves fundamentally differently from gas. Gas, as we have already said, interacts physically, through pressure, through shock waves. Dark matter doesn't do that. It interacts only through gravity. Therefore, when two galaxies collide, their dark halos literally pass through each other. They attract, slow down, eventually merge, but without shock waves, without heating, without shocks. This creates an amazing picture. At the moment of collision, gas and dark matter separate. The gas breaks, accumulates in the collision zone. Dark matter continues to move by inertia and moves forward. As a result, the center of the gravitational mass of the galaxy is shifted relative to the center of the accumulation of ordinary matter.
This is exactly what astronomers observed in the famous Bullet Cluster, a collision of galaxy clusters that has become one of the most convincing direct evidence for the existence of dark matter. X-ray observations showed the gas in one place. Gravitational lensing, a technique that allows you to map the distribution of mass, showed dark matter in a completely different way.
The division was clear and unambiguous. So when galaxies collide, we are dealing not with one process, but with three components that occur simultaneously and behave differently. Dark matter flows according to its own laws. Gas twists and heats up. Stars chaotically fly away in new orbits. This is not just a clash. It is a symphony of chaos with several instruments, each playing a different part. Now, let's talk about what is happening in the very center, because that's where the most dramatic thing unfolds. At the center of almost every large galaxy is a supermassive black hole. This is not a hypothesis. It is an observational fact confirmed by decades of research. At the center of the Milky Way is Sagittarius A star, a black hole with a mass of about 4 million solar masses. At the center of Andromeda is a hole of about 100 million solar masses. At the center of some elliptical giants are holes tens of billions of solar masses. In their normal state, these black holes are relatively quiet. They do not devour everything. They just don't have enough power, a gas that would fall close enough to the event horizon. Our Sagittarius A star is now in such a sleeping mode. It sometimes flares up slightly when it swallows a small gas cloud or a star that has come too close. But in general, it is a quiet and inconspicuous object. And now, the collision of galaxies. And everything changes. When two galaxies begin to interact, the gas loses angular momentum under the influence of tidal forces and gravitational perturbations. This key word is angular momentum. Gas orbiting does not fall towards the center because it has angular momentum, a kind of rotational inertial drag. If this moment is not lost, the gas simply continues to rotate. But when galaxies collide, perturbations disrupt this equilibrium. The gas begins to lose angular momentum. And as soon as this happens, it begins to fall to the center. Imagine a spiral. Gas moving in a wide orbit begins to narrow its trajectory under the influence of perturbation. Its orbit decreases. It moves closer and closer to the center. There is already another gas falling from the other side. They don't just fall, they spin. An accretion disk is formed, a flat, rotating structure around a black hole, heated to unimaginable temperatures. And this is where what astrophysicists call the activation of the galactic nucleus begins. An active galactic nucleus, or AGN, is a regime in which a supermassive black hole actively consumes matter and releases a colossal amount of energy in the process. This is one of the most powerful processes in the entire observable universe. As the gas falls into the accretion disk, it accelerates and heats up. It heats up very much, to temperatures of tens of millions of Kelvin. At such temperatures, the substance begins to radiate, not just in the visible range. It shines in X-rays, in ultraviolet, in the gamma range. The brightness of the active core can exceed the total brightness of all the stars in the galaxy combined. One small region, a few light hours in size, shines brighter than 100 billion stars. This is a quasar, one of the most exotic and powerful categories of objects in the universe. The name comes from the English quasi-stellar object. Initially, they looked like stars in photographs, but then it turned out that they were galaxies with monstrously active nuclei at distances of billions of light years. Quasar activity peaked about 10 to 12 billion years ago, when the universe was young and galaxies collided much more frequently. Now there are fewer quasars because there are fewer collisions and there is less gas in galaxies. But they still exist. And in galaxy clusters, where the density of objects is higher, collisions, and thus the activation of nuclei, are still occurring today. But activating the core is not just about glowing, it's also feedback. And it is through feedback that what can be safely called a space tornado begins. As the accretion disk orbits the black hole, the magnetic fields around it spiral into a spiral. This is not a metaphor. This is a real physical process. The plasma falling into the hole is itself a conductor, and its motion creates magnetic fields. These fields twist, strengthen, and concentrate along the axis of rotation. And at some point, they literally shoot out. Relativistic jets burst out along the poles of the black hole. Relativistic means moving at a speed close to the speed of light, sometimes 90, sometimes 99% of the light. These are streams of plasma, ionized matter that fly out of the polar regions of the accretion disk and go into intergalactic space at distances of hundreds of thousand light years, sometimes millions. The length of such jets often exceeds the diameter of the galaxy itself, dozens of times. The galaxy M87 in the constellation Virgo is one of the most studied examples. Its jet is visible in the optical range and has a length of about 5,000 light years. This is an impressive object in itself. But in radio wavelengths, the structure created by Jet M87 stretches for hundreds of thousands of light years. It was this galaxy that the world recognized in April 2019 when the Event Horizon Telescope took the first image of the shadow of a black hole. Then, everyone saw the famous orange ring, the glow of gas around the event horizon of a black hole with a mass of 6.5 billion solar masses. But let's get back to jets. A jet is not just a stream of plasma. This is a whole system of interactions. When it crashes into intergalactic gas, so-called radar blades form at its end. Huge bubbles of hot gas pumped there over millions of years. These blades press on the surrounding intergalactic gas, heat it up, prevent it from cooling and falling back into the galaxy.
This is the feedback mechanism. A black hole feeding on gas simultaneously destroys the possibility for further feeding because its jets heat up and accelerate the very gas that could have fallen into the accretion disk. At some point, the gas runs out. The activity of the nucleus decreases. The jets weaken. The gas begins to cool again, and the cycle can repeat. Such cycles of on and off of the active nucleus are observed in the X-rays of galaxy clusters. In the gas envelope of the clusters, cavities are visible, bubbles blown out by old jets. They are sometimes referred to as ripples of the universe, traces of long-ago bursts of activity, frozen in intergalactic gas.
And now, the most visually exciting, what can rightfully be called a space tornado. When two galaxies merge, gas doesn't just fall toward the center and form an accretion disk. It does this on very complex trajectories. Gas from one galaxy rotates in one direction. Gas from another, possibly to another, or at an angle.
When these flows meet, turbulence of colossal proportions begins. In astrophysics, this is called gas dynamic turbulence. The streams twist and form vortices. Vortices of different scales are nested inside each other. Huge vortices break up into smaller ones, those into even smaller ones, up to scales where the viscosity of the gas finally dampens the motion.
This hierarchy of vortices is a classic sign of advanced turbulence. If we could observe all of this up close in time-lapse footage, we would see something very similar to a terrestrial tornado. Only instead of air and water vapor, ionized hydrogen and helium. Instead of kilometers, there are thousands of light years.
Instead of minutes, there are millions of years. And instead of a wind of 500 kilometers per hour, there are plasma flows with speeds of hundreds and thousands of kilometers per second. These gas dynamic vortices do several things at the same time.
Firstly, they mix gas of different origins. Gas from two merging galaxies combines and acquires common properties. Secondly, turbulence heats up the gas. The mechanical energy of the vortices turns into heat. Thirdly, vortices provoke local compressions. In the nodes of the turbulent structure, the gas condenses, and new stars can flare up there.
But it is especially interesting that turbulence is able to carry angular momentum, and this is critically important. It is through turbulent vortices that the gas eventually loses angular momentum and falls to the center, feeding the black hole. That is, turbulence is not just chaos. This is the mechanism through which chaos feeds the most powerful object in the galaxy.
There is another important effect that is worth talking about separately. These are galactic winds. When the nucleus is active and the jets are powerful, they don't just escape outward into intergalactic space. They interact with the interstellar gas of the galaxy itself. They push him. They disperse. They eject entire streams of matter from the galaxy.
The galactic wind is exactly what the name says, a stream of gas leaving the galaxy. Only the speed of this wind is hundreds and thousands of kilometers per second, and the volume of matter removed is millions of solar masses per year. Galactic winds are observed not only where the core is active, they also occur during starbursts, when a huge number of supernovae explode in a short time, and their combined pressure literally blows gas out of the galaxy. In star-forming galaxies undergoing mergers, both mechanisms can work simultaneously, both powerful winds from the core and winds from supernovae. This creates a complex multi-level picture. Hot gas, accelerated by the jet or the pressure of explosions, goes out. Cold gas is pulled to the center. At the boundary between hot and cold, there are new shock waves, new regions of compression, and new stars. All this is intertwined into a structure that can hardly be described in words. It has vertical flows and horizontal flows, twisted spirals and sharp fronts, hot bubbles and cold threads. If you superimpose all this on visualization, you get something that literally takes astrophysicists' breath away.
Now let's talk about real observations. Because everything described above is not just a theory. This is what we see through telescopes. Let's start with the already mentioned antenna galaxies, NGC 4038 and NGC 4039 in the constellation Raven. This is perhaps the most famous example of a galaxy collision that can be found in any astronomy textbook. Two long, curved tails, tidal tails of stars and gas, give the system a resemblance to insect antennae, hence the name.
The distance to the antenna galaxies is about 45 million light-years. It's close enough to see the details. And what we see is chaos in action. X-ray observations from the Chandra telescope have revealed hundreds of bright point sources, X-ray binaries, and regions of active star formation.
Infrared observations revealed dense clouds of dust heated by young, massive stars. Radio observations have revealed extensive structures of hot gas. It is estimated that the antennae galaxies began interacting several 100 million years ago. They have already passed the first periapsis and are now in the intermediate stage. In a few 100 million years, they will finally merge into one elliptical galaxy. Another example is the Mouse Galaxy, or NGC 4676. It is a pair of colliding galaxies in the constellation Canes Venatici, about 300 million light-years away. Their name is explained by their shape. Each has a long, thin tidal tail, making the pair look like two mice with tails. This is a slightly earlier stage of interaction compared to the antennae. The galaxies have just passed the first periapsis and are starting to diverge before the second collision. But
modeling this system makes it possible to reconstruct the history of interaction and predict the future quite accurately. According to calculations, in a few 100 million years, they will also merge. Let's move on to a more exotic example. Stephan's Quintet is a compact group of 5 galaxies in the constellation Pegasus. 4 of them are about 290 million light-years away and are actually interacting. The 5th is visually in the same group, but much closer to us, and is not related to the others. Stephan's Quintet was one of the first objects to be studied in detail by the James Webb Telescope after its launch. The image
published in July 2022, showed unprecedented details: shock waves between colliding galaxies, streams of hot gas, regions of intense star formation. Filaments of molecular hydrogen, a cold gas, are visible, which stretch over vast distances in the shockwave zones. It is a complex, multi-layered structure in which hot gas in X-rays, warm gas in the infrared, and cold molecular clouds in the radio range are simultaneously visible. Stephan's quintet demonstrates another important thing. When collisions in groups of galaxies occur, the processes do not occur in isolation. One interaction leads to another. Shock waves from one pair of galaxies heat up gas that would otherwise power a third galaxy. Gas blown out of one galaxy by the wind or jet settles on another. Everything is connected to everything. It is impossible not to mention the bullet cluster. Official name 1E0657-558. This is not a collision of two separate galaxies, but a collision of two entire clusters of galaxies. The distance is about 3.7 billion light-years. Observations of this system have become legendary in astrophysics, and it is here that the most convincing direct evidence for the existence of dark matter has been obtained. X-ray observations by the Chandra telescope have revealed the hot gas of the clusters. It has clearly shifted and concentrated in the center after the collision, forming a characteristic bullet shape. The gas slowed down due to pressure and shock waves, but the analysis of gravitational lensing showed that the bulk of the clusters, that is, dark matter, continued to move through, almost without slowing down. The separation of gas and dark matter can be seen in the images literally spatially.
This was the moment when a theoretical assumption turned into an observational fact. Dark matter does not interact with ordinary matter through pressure, only through gravity. Another class of objects that deserve special attention are ultraluminous infrared galaxies, or ULIRGEs. These are galaxies that shine brighter than 1 trillion suns in the infrared. Trillion. Most of them are the result of galaxy mergers, where huge amounts of dust and gas collapsed and began to give birth to stars at an incredible rate. The dust absorbs ultraviolet and visible radiation from young stars and re-emits it in the infrared. A classic example is ARP 220, located about 250 million light-years away. This is the result of the merger of two spiral galaxies. At its center, star formation occurs at a rate of about 200 solar masses per year, which is 100 times greater than in our galaxy. There, apparently, one or two nuclei are active, possibly both. ARP 220 is a living laboratory in which you can study all the processes described above at the same time. Now let's talk about jets in more detail, because jets deserve a separate conversation. They are a separate world in themselves.
Relativistic jets from active galactic nuclei are among the longest cohesive structures in the universe. The largest known jet belongs to the Alcyonius Galaxy, a giant radio galaxy 3 billion light-years away. The length of the radio structure created by its jets is about 16 million light-years. That's 160 times the diameter of our Milky Way. 16 million light-years. Light passes through this structure in 16 million years. The jets in M87 are perhaps the most studied. Due to the proximity of the galaxy and the brightness of the jet, it was possible to trace it at different scales. At the very beginning, literally at the base, on the scale of thousands of gravitational radii of a black hole,
the Event Horizon Telescope managed to resolve it. There is a connection between the accretion disk and the beginning of the jet. This is an unprecedented level of detail. As you move away from the nucleus, characteristic nodes are visible in the jet, bright concentrations that move at visible superluminal speeds. This so-called apparent superluminal motion is an optical illusion that occurs when an object travels at nearly the speed of light, almost in our direction. Light from different points in its trajectory reaches us with different delays, and the object appears to be moving faster than light. In fact, no. But it's a reminder of how relativistic jet physics is. How exactly jets are formed is one of the hottest questions of modern astrophysics. The answer is still not fully understood, but the general mechanism is as follows. When gas falls into the accretion disk, it brings a magnetic field with it. This field is captured by the disk and begins to rotate with it. Rotation twists the ley lines into a spiral. The faster the rotation and the closer to the black hole, the stronger the twist. In the central regions of the disk, the magnetic pressure becomes large enough to collimate, that is, compress into a narrow beam, the outflowing plasma. The rotating event horizon itself may play an additional role. If a black hole is spinning, and most massive black holes seem to be spinning, it is spinning space-time around itself. This effect is called the entrainment of inertial frames of reference, or the lens-Thirring effect. It additionally twists magnetic fields and plasma, helping to form the jet.
Such a mechanism is called the Blandford-Zeinach process. It is the rotation of the black hole, according to many models, that is the engine that powers the jet. A black hole literally gives away some of its rotational energy through magnetic fields to the outflowing plasma. This does not mean that the hole stops instantly. This is a slow process, but it is real and it is colossal in terms of energy scale. Now let's talk about what happens when two active cores end up in the same system. This is called a double active galactic nucleus, and it is one of the rare but observationally confirmed phenomena. When two galaxies, each with its own supermassive black hole, begin to merge, both black holes first remain at great distances from each other,
each at the center of its original galactic bulge. As galaxies approach and merge, their black holes also begin to get closer. They lose energy through dynamic friction with the stellar medium and eventually form a gravitationally bound pair, a binary supermassive black hole. At this stage, they are separated not by millions of light years, but by thousands, hundreds, and then units of light years. And at this stage, they begin to emit gravitational waves, ripples in space-time predicted by Einstein and detected by LIGO in 2015. However, LIGO so far only feels the mergers of stellar mass black holes, tens of solar masses. Mergers of supermassive black holes will require much more sensitive and large-scale detectors. It is for the registration of such waves that the future LISA observatory, Laser Interferometer Space Antenna, is being built. These are 3 spacecraft that will fly in the shape of a triangle with a side of 2.5 million kilometers. Such a huge detector. The launch is scheduled for the 2030s. If all goes according to plan, LISA will hear supermassive black hole mergers throughout the observable universe. But so far, double active nuclei have to be searched for by optical and X-ray methods. Several such pairs have already been discovered. For example, the 0402 plus 379 system is a binary nucleus in a galaxy about 750 million light-years away, where the 2 nuclei are separated by only 24 light-years. This is the smallest distance of confirmed binary nuclei. The effect of a space tornado is not just a poetic name. This is real physics. And there is a particular type of observation that makes this expression particularly appropriate.
In some galaxies with active nuclei, so-called molecular fluxes are observed. Powerful emissions of cold molecular gas accelerated by the pressure of the nucleus or winds from supernovae. This gas moves at speeds of hundreds of kilometers per second, but at the same time remains cold. Temperatures are several tens of kelvins. How is this possible? The fact is that instabilities are formed in the zones of interaction between the hot nuclear wind and the cold gas of the disk. The hot wind goes around the cold clouds, tears them apart, and at the same time disperses the fragments.
A structure is formed that resembles clouds picked up by an earthly tornado. The hot stream carries cold fragments inside it. Whirlwinds of different scales, threads, nodes. All this is in constant motion. Observations by the ALMA interferometer, a network of radio telescopes in Chile's Atacama Desert, have made it possible for the first time to see molecular fluxes in several galaxies with sufficient resolution to study their internal structure.
In some systems, rotating rings of molecular gas are visible surrounding the active nucleus. In others, there are straight streams flying in different directions. Thirdly, there are intricate vortex structures where gas moves simultaneously in and out in different areas. This is a cosmic tornado, not a single structure, but a complex system of nested flows, vortices, and countercurrents, controlled by a combination of gravity, magnetic fields, radiation pressure, and turbulence. Let's talk about another important phenomenon: how the activity of the nucleus affects the entire galaxy as a whole. This mechanism is called AGN feedback.
This is one of the central themes of modern extragalactic astrophysics. That's the problem. If you just take cosmological simulations, simulating the evolution of the universe, and run them without taking into account AGN feedback, the result doesn't match the observations. In the simulations, there are too many large galaxies in which star formation is actively underway. In reality, the largest galaxies, the elliptical galaxies, almost never give birth to new stars. They are red and dead. Something turned off star formation in them, and this something is exactly AGN feedback. When the core of a galaxy is active, it does several things.
First, its radiation heats the gas. X-ray and ultraviolet photons ionize the gas and increase its temperature. Hot gas is more difficult to compress, more difficult to form molecular clouds, and more difficult to give birth to stars. Secondly, the jets mechanically heat the gas in the halo of the galaxy. We have already talked about this. Bubbles blown out by jets heat intergalactic gas in clusters and prevent it from cooling. Third, powerful winds from the active nucleus, not jets but wider streams of gas, can literally sweep gas out of the galaxy. In some quasars, the speed of such a wind reaches several percent of the speed of light, and the power is comparable to the total radiation of 1 billion suns.
All this together leads to the fact that the galaxy is deprived of its fuel, gas. Without gas, there are no stars. Without new hot stars, the galaxy quickly turns red. Old red stars live a long time, and new blue stars are not born. A few billion years after star formation is turned off, the galaxy looks much like a typical large elliptical galaxy looks like today. This is the result: the merger activation of the core, feedback, the cessation of star formation, a red, dead ellipse. This scenario is called quenching, and it is AGN feedback that is considered the main mechanism that triggers it. Of course, in reality, everything is not so linear. There are nuances, there are exceptions. There are galaxies where the merger has taken place, but star formation has not stopped. There are quasars without obvious fusion. There are elliptical galaxies with no signs of an active nucleus in the past.
Astrophysics is not a textbook with unambiguous answers. It is a living science in which answers to some questions give rise to new questions. But the big picture, galaxy mergers as a trigger for nucleus activation and as a cause of star formation quenching, is now supported both theoretically and observationally. New data continue to arrive. The James Webb Telescope, which began work in 2022, has already given astronomers the opportunity to observe galaxies in the first hundreds of millions of years after the Big Bang. There, in an era when galaxies were densely packed into a relatively small space, mergers were the norm, not the exception. And there we see quasars, bursts of star formation, huge tidal structures. It was then that the structure of the universe that we see today was laid.
Now let's talk about the future of our own galaxy, about what awaits us. The Milky Way and Andromeda are, if you will, two galaxies that are already doomed to merge. The word condemned sounds ominous, but it basically just means that gravity has already decided everything. They fly towards each other, and eventually they will meet. According to astronomers' estimates, based on observations from the Hubble Space Telescope and the Gaia Space Telescope, the first periapsis, the closest approach, will occur in about 4.5 billion years. It sounds like a distant future, but if you look the other way, the Earth is also about 4.5 billion years old now. That is, this is about the same time as has already passed since the birth of the solar system.
What happens in a collision? For most models, it is the same as we described above. Tidal tails, a burst of star formation, possible activation of one or both cores. A few billion years after the first pass, the second one, then the third. And as a result, a merger into one large elliptical galaxy. This new formation is sometimes called Milkomeda, or the Andromilky Way. A little clumsy words, but they convey the essence correctly. The future galaxy will be larger than both of its parents and will have a fundamentally different shape. And what will happen to our sun?
What will happen to the Earth? Almost certainly nothing catastrophic. Stars, as we have already said, practically do not collide. The chance that our sun will be in the path of another star from Andromeda is vanishingly small. According to some calculations, the probability that the sun will change the galaxy altogether, that is, move from ours to Andromeda or be on the periphery, is several percent. But physically, nothing terrible will happen to him. However, one important change will happen for sure. The night sky will be different. If there were intelligent observers on Earth in 4.5 billion years, they would see something unimaginable. Andromeda will first look like a blurry spot. Then it will grow, taking up more and more space in the sky. A few million years before the collision, it will occupy a huge arc of the sky. The Milky Way, our native strip, will also be visible, but already distorted. The night sky will be overflowing with stars, much denser than it is now, because the interstellar distances in the central regions of merging galaxies will decrease. But all this is in the very distant future. Until then, the sun will have already turned into a red giant and swallowed the Earth, so there will most likely be no observers there, at least on Earth.
However, the Milky Way has other neighbors with whom it interacts right now.
These are dwarf satellite galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are two of our closest moons visible to the naked eye in the southern hemisphere. They're located at a distance of about 160 and 200,000 light-years, respectively. According to modern data, they are most likely flying past us for the first time. That is, they have not yet been captured by the gravity of the Milky Way, or there were but only for the last time. Their interaction with the Milky Way has already left traces. The Magellanic Stream, a giant band of gas that stretches from the Magellanic Clouds across half of the sky, is a trail of tidal interaction. This gas was pulled from dwarf galaxies by the Milky Way's gravity.
In addition, in 2003, the Sagittarius Dwarf Galaxy, a satellite of our galaxy, was discovered, which is being torn apart and swallowed up by the Milky Way right now. Its stars are scattered in a huge orbit around our galaxy. In fact, we're witnessing a small merger right now. Not an epic duel between two equal rivals, but the absorption of a much smaller object. And this is a typical story. Large galaxies grow by absorbing small neighbors. This is called hierarchical merger, and it is the main mechanism for galaxy growth in the standard cosmological model.
There is another class of processes that deserves to be mentioned: the interaction of galaxies without a direct collision. The so-called flyby encounters. Sometimes galaxies pass close enough to warp each other through tidal forces, but do not collide directly or merge. The result of such interactions can be polar ring galaxies, objects in which stars and gas rotate in two mutually perpendicular planes. It literally looks like a ring crossing the galaxy at right angles. Such structures arise when one galaxy captures gas from another, but the trapped gas falls at a different angle relative to the original disk.
Another example is ring galaxies. The Cartagena galaxy, better known as the Cartwheel, is one of the most prominent examples. A small galaxy pierced its center, and the blast wave from this collision spread outward, squeezing the gas in its path. The result is a ring of active star formation with a diameter of about 150,000 light-years, spreading at a speed of several hundred kilometers per second. The variety of shapes that galaxies take in the process of interactions is amazing. No two mergers are exactly alike. Each is defined by a unique combination of masses, velocities, orientations, gas, and dark matter composition.
Let's return to the question of how exactly scientists study all this, because the observation of one particular merger is always a snapshot of one moment. We can't watch one system go all the way from the beginning of the interaction to the final merger. It takes billions of years. We observe different systems at different stages and form a picture of them. It's like studying the life cycle of a tree, looking at a seed, a seedling, an adult tree, and a withered trunk in a single moment, and reconstructing the growth history from those pictures. The method works, but requires caution.
In addition to observations, astrophysicists widely use numerical modeling. Modern simulations are able to track the behavior of billions of particles in merging galaxies, stars, gas, dark matter. Supercomputers make it possible to reproduce in detail what happens in a collision and check whether the result matches what we see in telescopes. The largest of these simulations, the Illustris project and its successor, Illustris TND, reproduce the evolution of a representative volume of the universe from the Big Bang to the present day. They show individual galaxies, their mergers, the formation of tidal tails, bursts of star formation, and the activation of nuclei. And all of this is consistent with observations at a surprisingly high level,
although the nuances of AGN feedback are still the subject of intense study. Let's talk about one phenomenon that connects everything together and often remains behind the scenes, on the role of magnetic fields. Intergalactic and interstellar space is permeated by magnetic fields. They are weak, billions of times weaker than the Earth's magnetic field, but they are everywhere, and they play an important role in galaxy collisions. First, magnetic fields help keep the filaments of gas from decaying. In collision zones, the gas forms long, thin filaments, and it is the magnetic pressure along the filament that helps it retain its shape. These filaments become places of intense star formation. Second, magnetic fields affect turbulence. Magneto-hydrodynamic turbulence is different from ordinary gas dynamic turbulence. It is anisotropic, that is, it is not the same in different directions. It transports energy and angular momentum in a different way. Understanding magnetic fields in mergers is one of the urgent tasks of observational astrophysics. Thirdly, it is magnetic fields that underlie the mechanism of jet formation, as we have already said. Without them, there would be no accretion in its current form, no jets, and no related phenomena. Magnetic fields in distant galaxies can be observed through the polarization of radio emissions. ALMA, the Carl G. Jansky Very Large Array, and other instruments are providing increasingly detailed maps of polarization in mergers and active galaxies. This is still a young region, but the results are already encouraging. Another important question is, what happens to the intergalactic space itself around merging galaxies? Galaxies do not live in a complete vacuum. The space between galaxies and clusters is filled with so-called hot intergalactic gas. Its temperature is tens of millions of kelvins. This gas is visible in X-rays and makes up most of the normal matter in galaxy clusters, even more than all the stars in galaxies combined. When galaxies merge in a cluster, it disturbs the intergalactic medium as well. Shock waves propagate through it. Bubbles from jets press on her.
Winds from galaxies add metals to it, heavy elements synthesized in stars. That is why intergalactic gas does not consist of pure hydrogen. It contains iron, oxygen, silicon, and other elements. All of them got there through the galactic winds over billions of years. In a sense, all the intergalactic gas in the cluster is an archive of the history of all the interactions that took place there. Its temperature structure, chemical composition, and degree of turbulence all carry information about past events.
Now let's talk about gravitational waves in more detail. It's a topic that has opened a whole new window into the universe in recent years. In September 2015, the LIGO detectors detected the first signal, gravitational waves from the merger of two stellar mass black holes. It was an event GW 150914. The waves carried information about the merger of two black holes with masses of about 36 and 29 solar masses, which occurred about 1.3 billion light-years away. Since then, LIGO, Virgo, and CAGRA have recorded hundreds of events, mergers of black holes, neutron stars, and mixed systems. Each event is a short burst of gravitational waves, lasting a fraction of a second or a second. Mergers of supermassive black holes will produce waves of a completely different nature. Not momentum, but a long sine wave with an increasing frequency that can last for millions of years. It is impossible to detect it from Earth. The LISA detector is needed in space and with a base of millions of kilometers. But there's another way to hear supermassive black hole mergers, right now. This is the pulsar timing lattice.
Pulsars are neutron stars that rotate at tremendous speed and emit radio pulses with astonishing regularity, more precisely than many atomic clocks. If a gravitational wave passes through the space between the Earth and the pulsar, the regularity of the pulses is slightly disrupted. Very little, but measurable. In 2023, several international collaborations at once, Nanograv in the United States, EPTA in Europe, PPTA in Australia, and CPTA in China, published results that strongly indicate the detection of background gravitational wave radiation.
This is presumably the total signal from thousands of supermassive black hole binaries throughout the universe, gradually approaching and merging. In other words, it is the background whisper of countless galaxy mergers, recorded in deviations from the regularity of pulsar pulses. This is one of the most important observational results of recent years, and it is directly related to the topic of our conversation: what happens when galaxies collide and their nuclei come closer?
Let's go back to the merger process itself for a moment and talk about timescales, because it's easy to underestimate them. The first close approach of two large galaxies, the first periapsis, takes several 100 million years from the moment when they are several 100,000 light-years apart. After that, they diverge, are slowed down by gravity, and approach each other again. Each successive pass is slower and closer than the previous one because the system loses energy through dynamic friction. The total time from the beginning of the interaction to complete merger is from 1 to several billion years, depending on the masses, velocities, and orbital parameters.
This means that most of the mergers we are currently seeing are events that began when the Earth was just forming, or before. We see the middle of the process. The beginning and the end are beyond our ability to observe in a single object. That is why statistics are so important. With a large sample, thousands of galaxies at different stages of interaction, it is possible to reconstruct evolution. Major sky surveys, such as the Sloan Digital Sky Survey, have given astronomers just such a sample. And the future survey of the LSST on the Vera Rubin Observatory, which began work in 2025, provides even more.
Now let's talk about what happens at the end of the process, when the two nuclei finally come within a few light years or less. This is the so-called last parsec problem. This is what it consists of. Dynamic friction with the stellar medium effectively slows down the approach of two black holes at great distances. But as they get closer, there are fewer and fewer stars available for braking. Their sphere of influence is exhausted, and the process of rapprochement is slowing down. Black holes need to somehow get close enough for the emission of gravitational waves to become effective. And this requires distances of the order of thousands of a parsec. That is, several light days.
It's time to talk about what it's like to live in a galaxy that is undergoing a merger. More precisely, what it would be like. If intelligent life existed on a planet in one of the colliding galaxies, say the same galaxy, ARP 220, what would it observe? The first and most obvious change? The sky would become much brighter. Bursts of mass star formation produce huge numbers of young, massive blue stars. They live for a short time, a few million years, and die as supernovae. Supernovae explosions would occur much more frequently than in our current galaxy. The Milky Way has about 1 or 2 supernovae per century. In a starburst galaxy, this could be several per year.
Each close supernova
is a potential threat to the planet's biosphere within a radius of several hundred light years. Gamma radiation can destroy the ozone layer. Several supernovae in a row over 1 million years is a serious environmental stress. But the most dramatic thing is the activation of the nucleus. If a bright quasar turns on in a galaxy, its radiation will be visible from anywhere in the galaxy. It's not a star in the sky, it's an object that shines brighter than the rest of the galaxy. Harsh ultraviolet and X-ray radiation will permeate interstellar space. For life on planets close to the core, this would be devastating. On the periphery, it is much less dangerous, but noticeable.
So, the collision of galaxies is not just beautiful. This is potentially one of the most life-hostile processes in the galactic environment. However, there is a downside. Galaxy mergers are not only about destruction, but also about construction. When intense star formation erupts in a collision, it's not just hot, massive stars that are born. Stars of all masses are born, including those like our Sun. And protoplanetary disks form around many of them. Planets appear. Moreover, massive stars, quickly burning up and exploding as supernovae, synthesize and eject heavy elements into the interstellar medium. Oxygen, carbon, iron, calcium, silicon.
Without these elements, there would be no rocky planets, no organic chemistry, and no carbon-based life. Each galaxy merger enriches the interstellar medium with heavy elements, and thereby creates the conditions for the next generation of planets and a potential biosphere. In a sense, our own planet and ourselves are the product of past collisions and interactions of galaxies. The iron in our blood and the calcium in our bones were synthesized in stars that flared up and went out long before the solar system was born. Many of these stars could have been born during the era of intense star formation caused by galaxy interactions in the early universe. Chaos, destruction, and rebirth are not a metaphor. This is a literal description of what is happening.
Let's talk about another object that deserves special attention: Centaurus A. Centaurus A, or NGC 5128, is about 13 million light-years away. It is one of the closest radio galaxies to us with an active nucleus. It is easily recognizable by the characteristic band of dark dust that crosses the bright elliptical body. This band is the trace of a swallowed spiral galaxy. Relatively recently, by cosmic standards, Centaurus A collided with a smaller spiral galaxy and swallowed it. The dust from this galaxy is still visible.
And right now, Centaurus A has an active nucleus. Its black hole, with a mass of about 55 million solar masses, is actively devouring matter. Jets are visible in radio, optical, and X-ray ranges. The length of the radio structure is more than 1 million light-years. Centaurus A is a living illustration of what we're talking about. The merger with a small galaxy led to the flow of gas to the core, which activated the black hole. Jets have been blowing into the environment for hundreds of millions of years. The dust of the swallowed galaxy is still visible. This is not a reconstruction, not a model, not a simulation. This is a real system that can be observed right now.
NGC 6240 is another outstanding example. This galaxy in the constellation Ophiuchus, 400 million light-years away, is the result of the merger of two galaxies, each with its own nucleus. X-ray observations by Chandra in 2002 revealed that NGC 6240 contains 2 active nuclei, 2 active supermassive black holes, separated by about 3,000 light-years. This is the first system in which 2 simultaneously active nuclei in the same galaxy have been unequivocally identified.
Both black holes absorb gas, and both generate X-rays. They are already within the same galaxy. The merger of galaxies has been completed. Now their nuclei are merging. In a few 100 million years, they will finally merge into one even more massive black hole. This final act of merging, the collapse of 2 supermassive black holes into one, is accompanied by a powerful burst of gravitational waves. These are the kind of events that Lisa will be looking for. Throughout this story, we have mentioned scales several times, and still you feel that the words do not convey the real meaning of these numbers. Let's try again.
The Milky Way galaxy contains about 200 to 400 billion stars. Its diameter is about 100,000 light-years. If we could travel at the speed of light, the highest possible speed in nature, it would take us 100,000 years to cross our galaxy. Not only a human life, but the history of human civilization will not be enough. Andromeda is 2.5 million light-years across. This means that the light we see from Andromeda today came from there 2.5 million years ago, when early human ancestors still lived on Earth. At that time, there was no language, no tools, no fire.
The jet galaxy Alcyonius is 16 million light-years distant. This is 6 times the distance to Andromeda. The observable universe is about 93 billion light-years in diameter. There are about 2 trillion galaxies in it. These are not just big numbers. These are numbers at the sight of which you understand that the human mind is literally not adapted to perceive them. We can write down these numbers. We can operate with them mathematically, but not to feel them. The neural architecture of the brain, formed for life on scales of kilometers and years, simply does not have the tools to do so. And yet, we are studying. We build telescopes, detectors, supercomputers. We develop theories and test them on data. We literally take light that has passed billions of years and read the history of galaxies in it. This is probably one of the most amazing things about human existence, that evolution has produced an intelligence capable of asking questions on the scale of the entire universe. Before moving on to the finale, I would like to mention one concept that gives all of the above an additional dimension. In recent years, there has been increasing discussion that AGN feedback, the very quenching of star formation by active nuclei, may not be just a physical process. A number of works have suggested that active nuclei perform a kind of regulating function in the evolution of galaxies. Not only do they destroy the gas, they also redistribute matter in space. Metals ejected from galaxies by winds fall into the intergalactic medium, from where they can then be captured by other galaxies.
This creates a kind of ecosystem in which galaxies exchange matter through outer space. Gas enriched with heavy elements can enter a nearby galaxy and become material for new stars. Dark matter from one halo mixes with dark matter from another when it merges. The entire large-scale structure of the universe, the web of filaments, knots, and voids that can be seen on maps of galactic surveys, is a trace of these processes that took place over 13.8 billion years. Every merger, Every jet, every galactic wind is a small contribution to this grandiose pattern. Now to the finale, to the reason for which, in fact, it was worth telling all this. When we look at the night sky, we see a static picture. The stars stand still. Galaxies are just blurred spots. Everything looks eternal and unchanging. But this is an illusion generated by the fact that our life is incomparably shorter than cosmic processes.
In fact, the sky lives. Galaxies are moving. They do. They merge. Their collisions give birth to new stars, new planets, new possibilities for chemistry, and perhaps for life. Their collisions awaken black holes that shine brighter than 1 trillion suns and throw plasma jets millions of light years away. In their gas, whirlwinds and tornadoes of unimaginable proportions are spinning. Their mergers shake space-time itself. And this is not somewhere far away in the abstract theoretical world. This is happening right now. As you read or listen to this, somewhere in the universe, 2 galactic nuclei are making another rotation towards the final merger. Somewhere, a jet crashes into intergalactic gas and blows out a bubble hundreds of thousands of light years across. Somewhere, a cold molecular flow rushes away from the galaxy at a speed of 1,000 kilometers per second. And in 4.5 billion years, this will happen to us. Our galaxy, the same streak of light in the night sky that all human ancestors have seen since the beginning of time, will meet Andromeda. Something will perish. Something will be born. Probably billions of years after the merger, there will be planets in the vicinity of the new elliptical galaxy. Planets formed from material that was part of our galaxy billions of years ago. Will there be life there? Will there be a mind that looks up to the sky and wonders about its origins?
We don't know, but the question itself is wonderful. The universe is not static. It is not safe. It is not designed with the convenience of the observer in mind. It is huge, seething, and indifferent. But it is in this turmoil, in collisions, explosions, vortices, and jets, that everything that makes our existence possible is born. Chaos is not the opposite of order. Chaos is what order is built of. And nowhere is this more evident than in space, when the galaxy descends into chaos.